Hello, in this video we're going to look at an example and we're going to match it up with our NPAT formula and see what we can figure out about this problem that is an exponential problem. So first off, I know it's exponential because I know that it fits this NPAT formula. And so writing that down helps me just match up the pieces of that. So I'm asked, what is the starting amount of this tritium? And I just look at what number is in place of P. So looking at my formula, I see that P would be 50. And reading up here, it tells me this is grams. All right. So is the tritium growing or decaying? How do I know? So whether it's growth or decay is determined by A. And as we summarized in our chart previously, if A is less than 1, it's decay. So this is decaying. How do I know? Because the A is less than 1. What does the 0.945 mean? So we know that exponential problems are when there is percent growth or percent decay. And so this decimal truly means a percent, and it means the percent remaining. So to change a decimal to a percent, I would take the 0.945 times 100, and that would give me 94.5, and that changed it to a percent, so 94.5% of the tritium remains. So this A value calculates what's left, not what is gone. Okay, so that can be changed to percent because we know that there's constant percent change in exponential problems. And so we change it to a percent by multiplying by 100, and it gives us what's remaining. Now it asks us, by what percent is the tritium growing or decaying? So there's two ways to approach this problem. First off, I know that it is decaying, so I'm just going to cross out the growing. By what percent is the tritium decaying? So the one way to look at this is to take 100%, subtract out the 94.5%. This is all working in percentages. And so that gives me an answer of 5.5%. So this is figuring out that it's different from 100 by 5.5%. Specifically, it would have started at 100. That's if it didn't grow or decay. 100% is that it would stay exactly the same. And 94.5% is left, so that means 5.5% decayed. Another way to do this is because I know that the 0.945 is the A value, and I know it's a decay equation, I can say that this A value in any decay equation is equal to 1 minus R, because that's how we get that A value in a percent problem. So if I do that, I have this little algebra problem, and then I can do the algebra. So that's more work, but it always works. So I subtract 1 from both sides, and I get negative 0.055 equals negative R. Divide both sides by negative 1, and that gives me R equals 0.055. And then I can multiply by 100 to change it to a decimal. So the R is 5.5%. So the algebra is kind of the long way to do the problem, but it always works. And the shorter way is just thinking about understanding that the decimal was the percent that remains, then I can subtract it to see what left. So 100% is the start. The 94.5% is what remains. And so the 5.5% is what decayed. So now I'm asked to rewrite this as a word problem so that I just see the connections. And so we had started with the 50 grams, so I would say 50 grams of this tritium are placed in a container. They will decay by 5.5% each year. And so I have then in words what I had seen already in the formula. And just connecting back, this is how we would have gotten the formula. We would have known these details about tritium.